Hello, it's Keith here. This is lesson 46 of the platform-specific series of my 68000 assembly programming tutorials, and we're looking at the X68000 today. We're looking at Mintail. Mintail is my multi-platform tile map. It originally came from the Z80, ported to the 6502, and now it's reached the 68000. So this has two parts. There's the multi-platform code, which is, of course, specific to a CPU, but it is common and runs on all the systems in the exact same way. And then there's the platform-specific code, which is what we'll look at today, and this is the part that does the actual drawing to the screen. Now the intention of Mintail is to write a piece of code that is working in basically the same way on all of the systems, so you could port a game between the systems in less time and hopefully with the same kind of functionality. And because Mintail works on systems with hardware tile maps and with just bitmap screens in the same way, it makes it easier to cope with that and allow the game to work in a similar way. It was originally designed for my Chibi Fighter Street Fighter parody, and that's why the graphics engine supports X flip, so we can horizontally flip our sprite. If I just press the fire button here, so now my sprite is turned around, but it doesn't at this stage support Y flip. The reason for that is I simply didn't have time to add as much functionality as I wanted. This is what's known as Mintail, and there's a successor I'm working on called Maxtile, which is also available for the Z80, currently porting to the 6502, and I intend to port to the 68000. It supports a lot more functionality, Y flip, transparency, fast fill, and various other things. So this is a kind of intermediary stage, a simpler version. I think it's worth looking at, but as I say, there will be more to come later. So let's go over to the code and let's take a look at what we've got for today's example. So here is the code for the Mintail example for the X68000. Now what we're not going to look at is the stuff we've covered in other tutorials. So how to read the joystick, how to set the screen up, how to actually sort of calculate the movement of an object around the screen by joystick keys. I've done that all in the simple series before. What we're only going to look at today is the new code related to this tile map drawing. So that's what we're going to look at only. So how does it work? Well, basically the way that the tile map drawing routines work is that they have these simulated software sprites and they also have the tile map, but they're actually both done by the same code. The Chibico character, that's my mascot, you can see in the corner of the screen down there, the Chibico character is actually a miniature tile map. So that's the Chibico character's tile map. And those zeros there are the empty tiles around the feet. So you can see there's empty tiles there around the feet. That's those zeros there. The background is this larger tile map here. And a zero in this would actually represent a part of the tile map that hasn't changed. You see, even though this 68000 has a lot of functionality, I don't actually use double buffering on this system, and the reason for that is the 8-bit system, some of them simply can't do it. So I've chosen to use only a single buffer, and you keep that on all the systems because it's the most limited functionality that's available in some cases. So a zero in this is actually effectively cache, and a zero in this means nothing has changed. Now, when it comes to drawing our objects to the screen, what we do is we calculate the starting draw position of our object, and then we draw in strips. So we start from left and move to right, then we move down and draw and draw and draw. So when we're drawing the entire screen, we use this screen base value here. So this is the screen base in memory, and then what we're doing here is we're effectively calculating the centering of our virtual screen. Our screen is 256 by 192, our virtual screen. That's because that's what's supported by the vast majority of systems, the MSX2, ZX Spectrum. Some systems like the CPC have a larger screen, but it's more convenient to work at that more limited screen resolution and not worry about the extra space, because that way we don't have to worry about changing our screen calculation code when we're porting to lots and lots of systems. So we're centering the screen there. That's what we use when we're drawing the entire screen. When we're just drawing part of the screen though, we use this get screen pos calculation. This takes an X and Y value in D1 and D2. Now, in all of my tutorials now, I'm using a common coordinate system of pairs of pixels, logical units. So one logical unit is 2 pixels. And effectively, because our tiles are 8 by 8 pixels, 4 logical units equals 1 tile. Now, on the X68000, irrespective of the color depth of the screen and things, actually each pixel uses 2 bytes. It always uses 2 bytes. And so what we're doing here is we're multiplying the number of pixels effectively by 2 here, also converting from logical units to pixels. And so that is our X offset, and our Y offset, we need to multiply our Y line by 1024, and that's what we're doing here. We're then adding this to our screen base, plus our centering offset for, as I say, we're using a virtual screen where basically that is the top corner, although there are a few extra lines at the very top there. That's what we're doing there. So this returns A6 for our VRAM destination when we want to calculate the position of one of these simulated sprites. That's what we're doing there. Now, when it comes to drawing our objects to the screen, the multi-platform code, which there is a separate tutorial series on, that will calculate things like cropping, things like where the source tilemap data and how to break that up into strips. The actual platform-specific code is only these draw strip routines. So this will draw a strip to the screen. Now, A2 is our source tilemap. A5 is our source bitmap data in memory. A6 is our VRAM destination. And D7 is our width of our tilemap strip, because we don't, in this code, care about how many strips there are. It's the other code that's doing that job for us. So what we're doing here is we're loading our tile number into D0, a single byte tile number. If that is a 0, then we're not going to do anything. That's either a transparent part or an empty part of the cache. If it's not 0 though, we're going to draw it to the screen. And next what we're doing is we're checking the tile clear flag here. If this is a 0, then we are going to leave this unchanged, and that would be for if we're drawing our sprites to the screen. If we cleared the sprite tile map data, we wouldn't know what to draw next time, so we're not doing that. But if it's the background, then we do want to clear that, and that's what we're doing here. We're using it, clearing that byte of the tile, because we're then going to draw it to the screen. Now, each of our tiles on this system is 32 bytes, and we're using 16 color tiles here, so we're multiplying our tile number effectively by 32 here. And then we're effectively adding A5, which is the memory address of our tile bitmap data. We can see that here. Where is it? Here is our source bitmap data here. So we would point either to test sprite for the background or test chibico for our chibico character, and that does mean that tile 1 of our mascot character there and tile 1 of our background are different bitmap data. So although we've only got 1 byte per tile, we can use separate tiles for every single object on the screen, so not necessarily as bad as it initially sounds. So here we've calculated our source data here, and now in A3 we have our source tile bitmap data. And so what we're going to do is we're going to transfer 8 lines. So we're loading D1 with a counter here. So that's 8 minus 1, because there will be an execution while D1 equals 0. So we're loading that with 7 for 8 lines here. And we're going to use D0 as our build-up. So what we're doing here is we're loading in a byte from A3, and we're only using 16 color graphics. So basically what we're going to do is we're going to take the top nibble first. So we're rotating that top nibble here, and we're moving that 16-bit value into A6 here. A6 is the VRAM destination here, and so D0 will contain the built-up value there. That's why we cleared it up here. So that's the first pixel there. As I say, pixels always use 16-bit values on this system. And then what we're doing here is we're loading the second pixel here, again from A3. You notice we didn't increment A3 here, we did here. Now the top nibble of that will actually contain some data, but this system won't actually use that data in this screen mode. It's a 16 color screen mode, so it will just ignore that extra data there. So we don't need to do any other kind of shifting there. And that has done the first pair of pixels there. We're then doing that again for the second pair of pixels, the third pair of pixels, and the fourth pair of pixels. So we've effectively incremented A3, our source pattern data, 4 times here for the 8 pixels. And we've written our 8 pixels to the screen. We've effectively moved 16 bytes in VRAM, as I say. Even though we're using only 16 color mode, we are using 2 bytes per pixel, so 16 bytes for our 8 pixels of our tile. Now we want to move down a line. There's 124 bytes per VRAM line, and we've transferred 16 bytes, so we're subtracting 16 there. So that's moving us down a line. And then we're decrementing D1, and while D1 is greater than or equal to 0, we're repeating and doing another line. And because it will execute even when D1 equals 0, we loaded 7 here, even though we wanted to run 8 times. So that will draw an entire tile to the screen. What we now do is we restore our VRAM destination. We move across the screen by 1 tile, effectively adding 16 to our A6 VRAM destination. We move across our source tile map by 1 tile, single byte there, A2 there, and then we decrement 1 from D7, which is our tile count. How many tiles are there in this strip that we're drawing? So that will repeat until we've drawn the entire strip to the screen. So that's how we're drawing our normal unflipped tiles. So that's how we're doing. Let's see. That's the unflipped tile, so that's how we've drawn that to the screen. But we can flip it around, we can X-flip it. Now how do we do that? Well, on a system like the X68000 where memory is not limited, we could simply store every single pattern X-flipped in memory. It would be completely viable on this system, but just for compatibility with the other systems, and because we can, because let's face it, processing power is also wildly abundant for us, we're actually going to flip it in real time. So that's what we're going to do here. So we've got this next tile reverse here, which will walk from right to left in the source tile map. It still draws from left to right, but for each of the tile patterns, it will flip the pixel data. So that's what we're going to do here. So we're loading our pattern number again, clearing it if it's a 0, if it's non-zero, and if we have been asked to do so by tile clear. We're then calculating the offset in our pattern data, which is the same pattern data, and then what we're going to do is we're effectively going to do flip each of the pixels in our source data. So what we're doing here is we're effectively moving to the last byte within our tile patterns. We're moving past the end of the line here of the source pattern data, and then we're moving backwards by 1 byte and loading in a byte into D0. We're then moving that straight to the screen, so we will effectively get the low nibble there. We're then loading it in again, this time not changing the A3 memory address, and this time we're shifting it to the right by 4 bits. That's the opposite of what we really did last time. If you look, here is the original. We rotated the first one and we incremented on the second and didn't rotate on the second one. This time we're incrementing on the first one here, and then we're rotating on the second one. And we're doing that 4 times, and that is flipping the data within the line of the bitmap. And then once we've done the line, so we've transferred 4 bytes, we added 4 here, and we then moved back to the starting memory address. So we need to move past those 4, and then we need to move to the end of the second line. And so what we're doing here is we're adding 8 to our source pattern data to do that. And then we are moving to the next line in VRAM, again adding 1024 minus 16 here, because our writes to the VRAM is still going from left to right as before. It's our processing of the pattern data and the tilemap data that is reversed. Okay, so there we go. So we've transferred an entire tile there that we've just repeated before until we've done an entire tile. We add 16 to A6 to move across the VRAM screen, but this time we subtract 1 from our A2 tilemap source, because we're working from right to left of our character bitmap data when it's X-flipped. So that's why we're subtracting 1 from A2 there, and we just repeat until we're done. It's not too difficult on a system like this with a very powerful processor to X-flip our data. It's on the 8-bit systems it gets a bit hairy, because sometimes the configuration of the bits within the VRAM is a bit tricky, and sometimes, well, in most cases, we have so little processing power available to us, we don't have a lot of options. But on the 68000 systems, we really have every option available to us, and so you could, as I say, store every single pattern X-flipped in advance. You could use a lookup table to do the conversion, or you can just do it in real time like this, and I think doing it in real time is just fine on this system. Anyway, we're going to come back to this kind of software tilemap thing. I'm currently working on a max tile version, which supports X-flip, Y-flip, transparency, a fast fill, and a bunch of other tricks. So far more advanced. This is really just an intermediary example. If you like what you've seen, please like and subscribe. Thanks for watching, and goodbye.